Hello everyone, myself is Dr. Vinay Kumar PN. I'm a faculty of mathematics from Sri HDD Government First Year College, Padvalaipe. Today we are going to write Maxima program for Green's theorem. We know that the Green's theorem says, suppose D is the region bounded by a simple closed curve C, then line integral of p dx plus q dy over C is same as double integral of dou q by dou x minus dou p by dou y dx dy over d, where p and q are functions of x and y. Now, let's see the first problem. So we need to write a maximum program for the function where p equal to xy plus y square and q equal to x square over the closed curve C, which is a curve which is bounding the region y equal to x square and y equal to x. Now that given p and q, let's partially differentiate p with respect to y. When you are partially differentiating with respect to y, you should note that your x should be treated as constant. So x will remain as it is, and the partial derivative of y is 1, and the partial derivative of y square is 2y with respect to y, and partial derivative of u with respect to x is 2x. And the region D is bounded by the curve C. Let us assume that curve C is partitioned into two curves, C1 and C2, as shown in the figure. Then D is nothing but the collection of all ordered pairs x and y, where your x runs from 0 to 1 and y runs from x squared to x. See this picture. Here, this is your curve y equal to x square, and this is your curve y equal to x. The point of intersection is at x equal to 0 and at x equal to 1 as well as y equal to 1. At this point x is 1 as well as y is 1. Now this is our actual region D, and it is bounded by these two curves. Let us say this one is C1 and this one is C2. This is oriented towards this, and this is oriented exactly opposite of this. Now let's write a program for this. We have already solved this one manually. Now let's write a program for this. What is that? Kilol. Let's call the function p of xy. You have to use assignment operator for that. What is that? What is that p? They are given x into y plus y square, that is x star y plus y square, and q of xy, that is also a function, so x square. And let's call f as a list, the list containing p of x comma y and q of xy. And see, along the curve C1, your y is equal to x square. So you know, in the case of line integral, we need to eliminate one variable and we have to express that one in terms of other. So let's make use of this one. Along the curve C1, your y is equal to x square. Therefore, dy is 2x dx. So let's replace y by variable x itself. So dx is nothing but differentiation of x with respect to x, whereas dy is nothing but differentiation of your y is x square, that is also with respect to x, so that whenever dy comes, it will differentiate x square, that is 2x, into dx. It will replace dy by 2x into dx. Let's call that one as a list dt, which is dx comma dy. Now let us find out the dot product of these two, that is f dot dt. You are multiplying two lists, so you need to apply dot product, so that you are going to get p of xy into dx plus q of xy into dy. That will be stored in h, that is your left hand side, p dx plus q dy. P of xy into dx plus q of xy into dy, that will be stored in h. And you should remember, we have to substitute what is our y in this. So let's substitute y is equal to x square in h. So wherever y comes, we'll replace that by x square. That will be stored in your h1. And now integrate this one, h1, so that your h1, and you should note that the limit for this line integral is x runs from 0 to 1, because you have eliminated the variable y, only x is remaining, so x runs from 0 to 1. So we'll get line integral of this, line integral of p dx plus q dy over c1. Similarly, find the line integral of p dx plus q dy over c2. Now, as usual, let's call dx, which is differentiation of x with respect to x, and we need to eliminate variable y. So dy is nothing but, here y is nothing but x, therefore your dy will be equal to dx only. So here you need to use this x and you have to differentiate with respect to x, so that this will be simply your dy is dx only. Now substitute that one in dt, make it as a list, that is dx comma dy, and already have f is nothing but a list, p of xy comma q of xy, so that your h will be dot product of these two, that gives you p of xy into dx plus q of xy into dy, that will be stored in h, that is your left hand side. And we need to substitute y equal to x, so let's substitute y is equal to x in h. So wherever y is there in h, that all will be replaced by x. Now integrate this, that gives you integration of p dx plus q dy over c2, that will be stored in I2. And actual line integral is line integral of p dx plus q dy over c, which is nothing but c1 plus c2. Therefore line integral I is line integral of this plus line integral of this, that will be stored in I. And let's find out what is double integration of this. So first let us find out partial derivative of this, and let's call this one as some s. So your s is differentiation of q of xy with respect to x, that is dou q by dou x, minus differentiation of p of xy with respect to y, that is dou p by dou y, dou q by dou x minus dou p by dou y. So we are calling that one as s. In fact, we need to find double integration of this over the region D. What is your region D? Here you should note that the region D is x varies from 0 to 1, but y varies from x squared to x. So your double integration will be stored in Z, that is integrate s where y runs from x squared to x, and integrate this answer with respect to x varying from 0 to 1. X varies from 0 to 1, y varies from x squared to x. Because here y contains x, so first we need to integrate with respect to y. So you know the Bodmer's rule, it says first you have to evaluate within the parenthesis. So it will evaluate first this answer, that is integration of this s, that is dou q by dou x minus dou p by dou y with respect to variable y varying from x squared to x, and after substitution it integrates with respect to x. So your double integration, right hand side is stored in z and left hand side is line integral, which is stored in I. We knew that if the Green's theorem holds, then these two must be same. So if I is equal to z, then print Green's theorem is satisfied, else print Green's theorem is not satisfied. In this way you can write a program to verify Green's theorem. Let's execute this one in Maxima and see what you're going to get. So as usual, we have written kilol, we called the function q, f and dx in the first line integral, that is over c1. Dx is differentiation of x comma x, and dy is differentiation of x square over x, because your y is x square. So you have to differentiate, your dy will become dx. So derivative of x square is 2x. Therefore, this will be 2x into dx. And let's call this one as a list dt, which is dx comma dy, and make dot product of these two so that you'll get pdx plus qdy, which is stored in h, and you have to substitute wherever y is there, that by x square. So h1 is substitution of y equal to x square in h. Now integrate this h1 where x runs from 0 to 1. Now similarly, line integral over c2. So there your y equal to x. Therefore dx is differentiation of x over x, and dy is your y is x. Therefore differentiation of x with respect to x gives your dy is nothing but dx. And make a list, and dot product of these two, that is pdx plus qdy, that will be stored in h. But you need to make substitution for y, which is x, y equal to x, so that h1 contains equation involving only variable x. And in C2, you should note that your x varies from 1 to 0. I2 is integration of h1 where x runs from 1 to 0. Integrate this. Your integrated answer I1 and I2, they are stored in I. That is our line integral pdx plus qdy. Let's find out the right hand side. That is double integral of dou q by dou x minus dou p by dou y. Let's find out first what is dou q by dou x minus dou p by dou y, and store it in S. That is differentiation of q of xy with respect to x minus differentiation of p of xy with respect to y in S. Now you have to integrate this with respect to x and y, but integration of S with respect to y, where y runs from x squared to x, first you need to integrate this, then you have to integrate that answer with respect to x, where x runs from 0 to 1. That will be stored in Z. So your Z contains right hand side, and left this I contains left hand side of Green's theorem. Now if these two are equal, then we say Green's theorem is satisfied. Else print Green's theorem is not satisfied. So if you run this one, you're going to get this. So this is one integral, that is a line integral over c1, and this is line integral over c2, and this is sum of these two, that is line integral over c1 plus c2, and this is double integral, and these two are equal to each other. Therefore Green's theorem is satisfied. Instead of displaying all these results, make judicious use of a dollar, so that your answer can be displayed in a very good looking manner. This is line integral over c1, this is line integral over c2, this is sum of those two, line integral over c1 and c2, and this is double integral. So these two are equal, therefore Green's theorem is satisfied. Similarly, I have given another problem where you have to write Maxima program. I have written a Maxima program, and we'll see. What is that problem? Write a Maxima program to verify Green's theorem for this function over the closed curve C consisting of coordinate axis and the lines x equal to 1 and y equal to 1. We know that coordinate axis means x equal to 0, this, and y equal to 0. They are coordinate axis. And they are given x equal to 1, so this line, and y equal to 1, this line. So all of they are intersecting here. Therefore, this region D is bounded by the lines y equal to 0, x equal to 1, y equal to 1, and x equal to 0. One curve, 2, 3, 4. So this is C1, C2, C3, C4. You should note that this is C1 in this direction, this is C2 in this direction, C3 in this direction, C4 in this direction. So your line integral pdx plus qdy over C can be partitioned into line integral over C1, C2, C3, C4. The total sum is line integral over C, and right hand side you can find it. Now let's write a program for this. What is your P? So kilol P of xy, call this one as a function. So we'll apply assignment operator x plus 2y, and q of xy is x minus 2y. You are written, and your f is list P of xy comma q of xy, and in the first curve, that is over C1 here, your y is 0. So your dy is 0. You know, in the case of line integral, we have to make one variable as in terms of other, that is eliminate y and write it in terms of x only. So when y is 0, dy is also 0. Now, so your x will remain. So dx is nothing but differentiation of x with respect to x, and dy is differentiation of 0 with respect to y. So that your dy will be simply 0. Now, let's call this one as dt. dt is list dx comma dy. Now your h, as we defined earlier, it is f dot dt, which gives you dot product of these two lists, so that this will be pdx plus q dy. That will be stored in h, but you know that you have to substitute y equal to 0, then only you can make the integration. So so that this becomes complete a function involving only x. So substitute y equal to 0 in h, then integrate this, and you know that in this curve your x runs from 0 to 1. So here x runs from 0 to 1, and in the second curve you should note that your x equal to 1. So you have to eliminate variable x, you have to retain only y, therefore dx will be 0, and you should note that your y runs from 0 to 1. Therefore, now let's write a Maxima code for this. dx, differentiation of your x is 1 with respect to x, and dy will remain as it is. dt is nothing but list dx comma dy. What is your h? F dot dt, that is pdx plus q dy. That will be stored in h, but you need to substitute x equal to 1 in that, so that all of your x will go off, only y will remain. Now integrate that h1 with respect to y, where y runs from 0 to 1. That gives you line integral over C2. Now let's compute line integral over C3, that is where y equal to 1. That means you have to eliminate variable y. Therefore your dy will be simply equal to 0. Now, and you should note that your x runs from 1 to 0. Here your x runs from 1 to 0. So let's compute that one. dx is differentiation of x with respect to x. dy is differentiation of 1 with respect to y. Now your dt will be list of dx comma dy, and as usual h is nothing but pdx plus q dy. That will be got by f dot dt. Now h1, you need to make a substitution of y equal to 1 in this, so that this contains only function involving x. Now integrate this with respect to x, where x runs from 1 to 0. Now let's compute line integral over last curve, that is C4. Here x is 0, that means you need to eliminate x, so you have to retain only y. When x is 0, dx is 0. And what is your y? Y runs from 1 to 0. Now let's compute it. Your dx is differentiation of 0 with respect to x, and dy is differentiation of y with respect to y. dt is list dx comma dy, and h is f dot dt, that is dot product of list f with respect to dt, so that you will get pdx plus q dy stored in h, but you need to make substitution of x equal to 0 in this. Therefore all the variables x will go off, only you will get a function involving variable y. Now integrate this with respect to y, where y runs from 1 to 0. That is your line integral over C4. Now add up all those, that is your line integral over C. So your capital I contains line integral over C pdx plus q dy. Now find out what is your dou q by dou x minus dou p by dou y. That is differentiation of q of xy with respect to x one time minus differentiation of p of xy with respect to y one time, and store it in S. Now let's find out the double integral over d. Integration of S with respect to y, where y runs from 0 to 1, x runs from 0 to 1. See this picture here, x runs from 0 to 1 and y runs from 0 to 1. Because they are independent of each other, you can write any one of them first. Your s is integrated with respect to y from 0 to 1 first, then it will be integrated with respect to x and with limits 0 to 1. That will be stored in z. And you know, the Green's theorem says if the line integral over p dx plus q dy is equal to double integral over d dou q by dou x minus dou p by dou y into dx dy, if they are equal, then print Green's theorem is satisfied. That is I equal to z, then print they are satisfied. Else print they are not satisfying the Green's theorem. Now let's execute that program. Kill all. P of xy is a function x plus 2y, q of xy is x minus 2y, and your f is a list of p and q, and dx. In the first case, we know that y equal to 0. Therefore, differentiation of x with respect to x, and dy is differentiation of 0 with y. And their list is stored in dt. And dot product of these two gives you p dx plus q dy, which will be stored in h. But we know that you have to make substitution for y, which is 0, so that all your variable will, y will go off, only x will remain. That is your h1. Integrate this with respect to x varying from 0 to 1. That gives you line integral over c1. And in the second one, we know that over c2, your x is 1. So dx is differentiation of 1 with respect to x. dy is this with respect to y. And this is list dt, which is dx comma dy. Dot product of these two, that is pdx plus q dy, is stored in h, and you have to substitute x equal to 1 so that your variable x will go off, only y will remain. That will be stored in h1. So integrate that one with respect to y varying from 0 to 1. This is your line integral over c2. And dx, a line integral over c3, where line integral c3 is y equal to 1. So dx, differentiation of x with respect to x, dy is differentiation of 1 with respect to y. That will be stored in dt as a list, and dot product of these two, that will be stored in h, which is pdx plus q dy, and you have to substitute y equal to 1, and that will be stored in h1, and your x varies from 1 to 0. Integrate with respect to this. That will be your line integral over c3, and it is stored in i3. And in the fourth one, your x equal to 0 over c4. Therefore, dx is differentiation of 0 over with respect to x, and dy is differentiation of y with respect to y. and your dt is list dx comma dy. Dot product of these two, that is pdx plus qdy, will be stored in h, but we have to substitute x equal to 0 so that it becomes a function of y alone. Now integrate this with respect to y, where y runs from 1 to 0, that will be stored in I4. So this is line integral over C4. Add those line integrals I1, I2, I3, I4, their answer, and store it in I. This is your line integral over C pdx plus q dy. And let's find out double integral over d. First we need to find dou q by dou x minus dou p by dou y. Differentiation of q of xy over x minus differentiation of p of xy over y. Difference of these two is stored in S. This is your dou q by dou x minus dou p by dou y. Let's integrate this with respect to y, where y runs from 0 to 1, and integrate this answer with respect to x, where x runs from 0 to 1, and store it in z. This is your double integral over d. Now if these two are equal, then we say Green's theorem is satisfied. That is, if I equal to z, then print Green's theorem is satisfied. Else print Green's theorem is not satisfied. So these are the answer which you are going to get. Remember, this is your line integral over C1. And this is line integral of pdx plus qdy over C2, over C3, over C4. So total answer, they have been stored, and these two are equal to each other. Therefore, Green's theorem is satisfied. This completes the writing of Maxima program on Green's theorem. Thank you.